Welcome back to Physics 151 Online. In class, we talked briefly about using approximation formulas based on Taylor series expansions that can sometimes be useful in evaluating a very complicated expression in a limiting case. And this allows us to check to see whether the complicated expression is consistent with the result that we get approximately in a limiting case that we already know what to expect as the answer. And so you've got a homework problem where you're asked to use one of these Taylor series expansion formulas. Actually, you may have to use a couple of different formulas in order to reduce a complicated expression to a limiting case. And I'd like to do a quick example to show how in particular you can use this binomial expansion formula for a quantity where you have 1 plus a small number raised to a power n. And we will be able to just keep the first two terms in this infinite series expansion to get a good approximation for the result of that formula. So what we can do is look at a very famous equation in the history of physics, and that is the formula for the kinetic energy of a very high-speed particle with mass m moving with speed v. You're all familiar, probably from a previous physics course, that the kinetic energy for a classical particle, where you have relatively large masses moving with slow speeds compared to the speed of light, that formula is just 1/2 mv squared. Well, one of the great developments of 20th century physics, right near the beginning of the 20th century, was that this formula, 1/2 mv squared, does not give an answer consistent with the law of conservation of energy if we look at collisions between high-speed particles. And so, although he was doing it for different reasons, Albert Einstein came up with a more general derivation of the kinetic energy of a particle moving with speed v that has a mass m. And what's curious about this expression is that it includes the symbol c, which is the speed of light. And in particular, the ratio of the particle velocity v over the speed of light c enters into this formula prominently. And it raises all kinds of crazy questions. Well, why should the kinetic energy of a particle moving with speed v depend on the speed of light? But it turns out that this expression is the more general expression consistent with observations that we do of particles moving at very high speeds. So the question is, does this really complicated looking expression, if we look at a case where v, the velocity, is small compared to the speed of light, does this expression reduce to the familiar 1/2 mv squared? Because it should, right? If 1/2 mv squared works for slow speed particles, then we should be able to take the more general formula that works for all particles at all speeds and see that it reduces to that in the limiting case. But it's not obvious. Just by looking at these two equations, they don't look at all alike. And so let's show how we can use the approximation formula for the binomial expansion to simplify this expression for the kinetic energy. That's the question. So let's see. To use the binomial approximation formula, I'm going to rewrite the expression for this relativistic kinetic energy by writing the square root in the denominator as a quantity to a power, to the power of 1/2. All right, so then how does that work? Well, it's actually 1 over the square root, right? So that means that we can replace the 1 over square root by 1 minus v squared over c squared raised to the negative 1/2 power. And the negative sign is there because this quantity was in the denominator. All right, so this then gives us an equivalent expression where we haven't made any approximations yet, but now it's in a form where we can see how to use the Taylor series expansion for the binomial expansion. Because if you look back on the original slide I showed, it said that if you have a quantity 1 plus x to the nth power, you can expand that in an infinite series, and if x is very small compared to 1, then what happens is every successive term in that infinite series gets smaller and smaller and smaller than the previous term. So we can take the 1 plus x to the n and approximate it quite nicely as simply 1 plus n times x, where n is the power. So how do we apply that to the case of the expression that we have for the kinetic energy? We've got this quantity in parentheses to the minus 1/2, and so just following this prescription right here for the 1 plus x to the n, this can be approximated as 1 plus, and the reason there's a plus is the minus 1/2 and the minus sign here get multiplied together. So it's 1 plus 1/2 v squared over c squared. And if that takes a few minutes to confirm that I did it the right way, just take the expression and use the prescription over here, 1 plus x to the n, as 1 plus nx, and you'll see that that's exactly what I get when I evaluate the expression approximately that's in the kinetic energy formula. So from this point on, we're almost done, because all we have to do now is substitute in 1 plus 1/2 v squared over c squared into the expression for the kinetic energy. And here's what we get. Okay, the kinetic energy becomes approximately now, in the limiting case where v over c is small, right? Because here the value x is v squared over c squared. So as long as v is small compared to c, that will make x small in this expression, and that's where it's valid. So 1 plus 1/2 v squared over c squared minus 1, well, look what happens. The 1's cancel out. And the 1's cancel out, leaving behind a 1/2 v squared over c squared times mc squared. The c squareds cancel out, leaving the familiar 1/2 mv squared as expected. Now, the fact that the more general expression that works for all speeds reduces to the classical expression that we're familiar with in the case of slow-moving particles, that gives us great confidence that these two expressions indeed are consistent with one another. And so it's a great technique to use if you have a rather complicated looking expression and you want to see approximately how it behaves. You can often use these approximation formulas to do that. And in addition to doing other kinds of checks about the consistency of units and whether an answer that you get makes physical sense, this is one more way that you can check the consistency of a physics equation to see if it makes sense in a familiar limiting case. I hope this is helpful, and I will see you in class.